Hello students, today I discuss about simultaneous and iterated limits. So let's start. First I have to subscribe this channel. If you have not subscribed, subscribe this channel. So let's start. We first consider AB open interval. There it is not an open interval, but a just fast bracket. There are a point in Cartesian plan. AB is a point in a Cartesian plan. This is AB, not open interval. This is the first bracket. This is a point in the Cartesian plan. So AB is the limit point. Limit point of a set of values in two-dimensional space. Part 2. This is the two-dimensional Euclidean space. Now, so first we understand what is simultaneous limits. If limit the point xy, any point xy is any point. Here I can take xy is any point is tending to the point. This is tending to the point AB. Tending to the point AB. And I have a function of two independent variables. A function of two independent variables. It is called actually simultaneous limit. It's called simultaneous limit. Now, if it happens that this is one kind, second kind, this is the iterated limit. This is if limit x tends to, there will be two limit applicable on a same function. Limit x tends to a and limit x tends to b. This is b. F is a function of two independent variables. This limit or this limit y tends to b and limit x tends to a. Function of f is a function of two independent variables. If such kind of limit we calculate, then these are called iterated or repeated limits. Iterated or repeated limits. There are two kind of limits. I will now provide a very important theorem in, in these two kind of limits, 1 and 2. So first, I write that what is the condition of existence of simultaneous limits. Existence of simultaneous limit. Simultaneous limit. So existence of simultaneous limit is that the simultaneous limit simultaneous limit of function fxy f and two independent variables xy exists exists and it is equal to a limit point a h the variables the independent variables tending to a point AB if for for every epsilon greater than 0 there exists a delta greater than 0 such that mod of the function f xy minus the limit point a mod always less than equal to epsilon for all values of xy x and y in the neighborhood of the neighborhood of FEB. It does mean that if you will take a Cartesian plan, two-dimensional Cartesian plan, xy, xy, then if there is AB point, then EB point, then in the neighborhood which is uh, in the neighborhood of AB, uh, the function, this is a function defined, this is fxy. So all the points in the neighborhood, in this neighborhood, all the points, this point, this point, this point, this point, this is neighborhood. So this is actually epsilon. This radius will be epsilon. It actually it is a straight line, not a circle. It is a straight line. So there will be epsilon both on the center from the both side. Epsilon distance from the point A, and there will be A minus epsilon, A plus epsilon, AB minus epsilon. Sorry, A minus epsilon, B minus epsilon, and there is a point A plus epsilon and B plus epsilon. In short diagram, A plus epsilon and B plus epsilon. These are the points on the Cartesian plan. In this neighborhood, in this neighborhood, this must happens that there will be a point A xy. Xy may be in this interval A minus B epsilon, A minus epsilon, B minus epsilon to A plus epsilon to B plus epsilon. The neighborhood of EB, xy take all the values, and this function must have a limit point, or the modulus of the difference must be less than epsilon. You can say it will tending to 0, tends to 0, where neighborhood of AB such that this will be actually delta. This will be delta. We have taken a delta for this purpose. This is also very small, tending to 0, just greater than 0, very small. A plus delta, A, A minus delta, B minus delta to A plus delta to B plus delta. There is the neighborhood of A, from A minus delta, B minus delta to A plus delta to B plus delta. The function have a limit point A, such that there will be a very small number epsilon, the mod of their difference from the limit point of the function less than equal to less than epsilon, tending to 0 for all values of mod of x minus A less than delta mod of y minus B less than delta. So this is actually in the diagram. This is the existence of condition of the existence of simultaneous limit. Now I am giving a theorem also. Theorem tells this states that we suppose that the simultaneous limit exists of fxy limit. The simultaneous limit extends to A, y tends to B of fxy exists exists and b equal to a. We are supposing, considering equal to equal to a, and let that the single limit x tends to a, where y is constant, y is a constant of fxy also exists in the neighborhood of b, exists in the neighborhood of b. Neighborhood of b. And also the reverse also means, if single limit will take y tends to b and x is constant, x is equal to constant in the neighborhood of a. This is x is constant of the single limit fxy. This is also exist. This also exists. Then in the neighborhood of a of a, then we can say that the iterated limit x tends to a limit. It does not mean that always iterated limits are equal. Y tends to b. So this theorem is very important, that here I am telling that iterated limits are equal. By this theorem we can say that both the iterated limit, this is the iterated limits, will change y tends to b, limit y tends to b if the conditions holds as I said in the theorem, then the iterated limits are found equal. Otherwise, generally iterated limits cannot found equal. These are equal, and it is equal to the simultaneous limit. This is the simultaneous limit. Limit x tends to a, y tends to b. Very important theorem. Must remember. In another video, I will give example of iterated and simultaneous uh, limits. So continue to watch, and if you have not subscribed, then subscribe to get these videos. If you like, then like. If you have any question, then comment me. I must answer. So thanks for watching. Have a good day.